Hi everybody. Today we are going to study about the library. This week also I chose some references from Wikipedia. Now you can read some different new terms about the library. In library lecture, the first topic is what is solid phase chemistry? And then we are going to learn what is combinatorial library. And using that concept, how can you build millions of molecules in your library? The key concept is one bead, one molecule the method. After you make such a huge library, next question will be how will you test those library molecules? After that, we are going to study also the biological library, not only chemical library. So the first topic is solid phase chemistry. If you think about conventional synthetic method, most likely we design that this way. We have a reaction vessel and heating block and also string bar inside and distillation tower on top. Can you guess what software did I use to draw this picture? Yeah, this is drawn by ChemDraw. So if you use ChemDraw, you can do many different things. Now in chemistry, especially the synthetic chemistry, usually the mixing is the easy part. After you are done with your chemistry, now next step is most likely separation or purification of your product. If that purification can be done by this type of extraction, maybe that's easier to approach. But most of those cases, you have a byproduct and also you have a leftover starting material, and most of those cases, we need to separate your product from different impurities by chromatographic separations. So usually this chromatographic separation requires you a lot of efforts and time. And if you make a very simple molecule like this, can you recognize what this molecule is? This is aspirin. One of those very popular the starting material, maybe the first organic reaction you can do in the laboratory or even during the high school days. Usually we do this reaction by adding acetyl group into this salicylic acid. So this is a simple reaction. Even after you did this, most likely you need to separate your pure aspirin from starting material of the salicylic acid using chromatography. If it goes quite big molecules like this, can you recognize this molecule? This molecule is a Taxol. Taxol is an anti-cancer drug which can attack microtubule structure. By over-stabilizing microtubule, it can interrupt the proper cell division, and it can be used very useful other cancer drugs. Molecule size-wise, molecular weight may be around 1,000, maybe bigger than usual drug like a small molecule, but the structure-wise, it's big, complicated with a multiple ring structure. Does not look like really monster like a molecule, but also making this type of molecule is quite difficult. So this first synthesis of this Taxol molecule has been published in Nature. Even though that's about 20 years ago, still the difficulties of making this type of molecule, this size of molecule, is still very, very challenging. And one of those heroes in this field is Casey Nicolau. He was a professor in Scripps for a long time. Several years ago, he moved to Rice. But anyway, he had a lab in Singapore too. And then his main job was making lots of these complicated molecules. Maybe this molecule, look at here, brevetoxin B, maybe biggest molecule human being ever synthesized by total synthesis of natural product. Anyway, making this type of molecules, usually it takes a lot of time and a lot of the manpower. So if your target is making this type of biologically active molecules, well, making one molecule can be more than challenging to finish your PhD. Then build up your own library, making many molecules, and then applying them into biological system can be totally impractical or too difficult to achieve. So that's why Instead of this solution phase chemistry, new approach can be solid phase chemistry. In solid phase chemistry, the key idea is you keep all the materials inside here. So usually you have some solid material. This material is usually synthetic bead, which can bind your the starting material or reagent, and then do all the reaction in this the setup. And then you can wash out and do the second step reactions and purifying your product. Everything can be done inside here by just washing and filtrations. So by using this solid phase chemistry, the key idea is to simplify all steps of purification, especially for the extraction or chromatographic separations. Remove all those tedious steps and simplify all the procedures by just the simple mixing, washing, filtration. That's the idea of solid phase chemistry. If you think about solid phase chemistry, maybe you think kind of big robots. $1 million of robots and automatically are moving around and then handling those reagents. So is it necessary to have this kind of robot to the solid phase chemistry? My answer is no. So sometimes we can use a different kind of robots, maybe student robot. When I said a student robot, okay, we don't need to have a highly educated, too sophisticated chemist doing this. So out of this picture, the two students are high school students and two students are undergraduate students. This picture was taken when I was working at NYU, New York University. So this is more than 10 years ago. So anyway, using these students, we could do quite decent the level of organic chemistry, the solid phase the chemistry. Usually the first step of doing the reaction is you need to measure exact amount of reagent. Using this the micropipette, we can deliver this reagent, exact amount of volume of reagent into these small vials. Also you can transfer resins inside here. Then here 4x6, this is 24 reaction vessel is ready to go. After you prepare these vials for reaction, and the next step is we need to provide activation energies. Most of those chemistry, even though you add those reagents, sometimes the reaction doesn't go. They need to overcome those activation energy. So we need to give those energy usually by heating. So this type of the heating blocks in biology, usually this has been used for heating up the buffers or enzyme reaction mixtures, but this can be used for chemical reaction too. So then you can put your reaction vessels in this heating the mantle. Then at least 24 or 48 or 96 reactions can be done very quickly. After all the reaction is done, now next step is filtering. By applying this reaction mixture which has resins and then filters through these the tubes. Then these tubes has this kind of the filtering fritz on the bottom, and then only reagent and solvents can pass through, resins can stay on top of here. After you apply those, and by applying the solvent, you can wash those excess amount of the reagent. After all the reaction is done, now these tubes can be immersed into acid solutions. Then this acid cleavage cocktail can cleave off those compounds and release into the solutions. After those cleavage is done, now the product can be collected in this receiving plate, and then all the materials can be released into the plate. So this is the usual step of starting from heating of those reactions in the bead. After reaction is done, now filtering and washing, and the final step is cleavage of those products and collect those products in this receiving other plate. If your reaction does not require any high temperature of activation energy, this step can be much easier. So here I will show you the small movie which can be much more accelerated and easier to manage. This movie was taken by my own lab at NUS. Enjoy.
The first step of the solid phase synthesis is the wetting of the resin. After wetting the resin, we add the dyes and the reagents. After the addition of the reagents, we place all the reactions in parallel into the shaker. After 12 hours, our reaction is completed, so we remove the excess of reagent. After removing the reagents, we thoroughly wash the resins with different solvents, mainly DMF, methanol, and DCM. Finally, the last step is the cleavage of our compounds from the resin. We mix the resin with an acidic cocktail, and we collect our products in label and separate vials.
How was the movie? That's quite interesting, wasn't it? So the reaction is quite easy, and you can manage tens or the 20s or even hundreds of different reactions in one step of the reaction setup. So practically you can manage 100 reactions, 100 product in one day of experiment. So this is the power of solid phase chemistry. So utilizing this solid phase technique, now we are going to move to so-called high level of high throughput synthesis using combinatorial chemistry.